Welcome back. So we have spent some time discussing about kinematics, how to visualize deformation in a flow, how different components of deformation matters when we are thinking of fluid dynamics. So now we are getting to conservation laws. So we have more or less the tools that we need, and we get started with conservation laws. And the first conservation law that we are going to look into, which is conservation of mass. So typically when you do conservation of mass for rigid bodies, the idea is in absolute sense, that you have rigid objects which are there, maybe a single one or an entity of rigid objects, and you think of conservation of mass in an absolute sense. Wherever there is a rigid body, you say that the mass is conserved, even if it fragments or there are two rigid bodies coming and joining together. You do that kind of a box counting to think of what conservation of mass is. When you do solid mechanics, again, like idea of conservation of mass is something which is not immediately what you think of. In fluid mechanics, because there is a flow that is constantly happening, at a given point in space is where you need an understanding of what conservation of mass is, because the stuff is always coming in and going out. So there is no such thing that you are preventing matter to leave or enter a domain. So if you are thinking of any problem in fluid mechanics, there is constant exchange of fluid matter. So how do we think of conservation of mass in that particular sense? So there are two ways of doing this, two ways of arriving at the conservation of mass. The first approach is based on what we have already done in kinematics. We encountered or we dealt with this idea of a material volume. So you can have a material volume or a material surface. So the idea means that if you now think of a material surface, that imagine that you have a region in space that is identified, and this region of space is made up of a whole bunch of fluid particles. Fluid particles, again, I should emphasize, this is not fluid molecules. You are just thinking of this mathematical abstract entity of a small enough point where you have sufficient number of molecules to define things continuously. So you have a whole bunch of these fluid particles, or you can think of them as tracers, which make up this volume V, and the space the surface is given by the surface S. So a material surface is where, if you were to just mark out few of these fluid particles at some instant of time. So what I am doing is, it's continuously made up of fluid particles, but I am just marking few of these fluid particles. So this is at time instant t equals 0. At a later time instant, this volume of space can become something completely different. So this is at t equals 0, this is at some later time t equals capital T, let us say. The volume need not be the same. So whatever are these fluid particles, they are being mapped to different points on this boundary. So they all get mapped to different regions. So what is happening is the flow, which you know as u of x comma t, that is the velocity field. It takes every point on the initial volume and maps it to this new volume. This new volume I will call it as V prime, which is bounded by a surface S prime. So for it to be a material surface, what it means is the points which were earlier on the surface continue to be on the surface. That is the idea of a material surface. For a material volume, whatever was enclosed, whatever fluid particles were enclosed in this volume, they continue to remain in this volume. With this idea of a material volume and material surface, we go back to in kinematics, when we were trying to understand ideas of deformation, we came across this concept of divergence. We saw that if there was a volume element, so if I define this as delta V, ddt of delta V, this was divergence of the velocity field. Okay. This strictly is, as I keep emphasizing, is in the limit of the volume element becoming infinitesimal. All these ideas are in the context of you having an infinitesimal volume element. So when you have an infinitesimal volume element, the rate of change of that volume element is related to the divergence. If you recall, the way we did this was we said you consider an infinitesimal volume element V naught, there is a transformation which was given by the Jacobian which took you to the new volume element V, and then we saw that the rate of change of that transformation of the Jacobian was related to the divergence, which is basically what I am writing here again. And again it is to be interpreted in the limit of that volume becoming infinitesimally small. So now for a material volume, if I write down the mass, so I considered that particular material volume that I had before. So this is some volume. I will now use delta V to imply that this is an infinitesimally small volume. Whatever is the mass that is contained inside this particular volume, that mass will not change with time if there are no sources or sinks of mass inside that region. So it is a material volume, nothing is exiting, nothing is leaving, it is acting as this region. So the boundary is evolving due to the flow, which means that whatever is enclosed continues to remain enclosed in that region. So this should be 0. Now the mass for this material volume I can write as rho in the limit of delta V going to 0. It is defined with respect to the density multiplied by that volume. This is again emphasizing implied for an infinitesimally small volume. Now if you expand this derivative, you have d rho dt times delta V plus rho ddt of delta V. This should be equal to 0. Now from our knowledge of kinematics, we know that a volume element is going to change based on what is the divergence. So if I make that substitution, I have delta V d rho dt plus divergence of u delta V rho is equal to 0. So I have written ddt of delta V from this relation as delta V times divergence of u. So if I take delta V outside, I have d rho dt plus rho divergence of u. Now this derivative that I have written out here with this time derivative ddt, the appropriate notation to use for this would be a capital D, because I am following that particular patch of fluid. I am basically tracking and moving along with it. So as the volume element evolves and turns into something else, let us say the volume element becomes something more complicated in shape in future, I am basically doing this measurement while following this volume element. So it is better to just keep that distinction. So I am going to write this as capital D dt of rho plus rho divergence of u. So this is a material derivative. So this quantity is a material derivative. Now this should be true irrespective of the choice of that volume element. This relation that I have here, this relation should be arbitrary with respect to whatever volume element that I have considered. So if that is to be true, then I arrive at a relation which is d rho dt plus rho divergence of u is equal to 0. This is my statement for mass conservation. It is also known as equation of continuity, implying continuity of mass, but just calling it mass conservation is sufficient, where the rate of change of density d rho dt plus rho divergence of u is equal to 0. Now you might still ask that this is obviously to be interpreted as following a fluid particle, but we know how to convert our material derivatives. We know that the material derivative can be written as d rho dt plus u dot del rho, that is the expression for the material derivative. That the material derivative can be written as the rate of change of that quantity at a particular point in space with time plus a term that is the rate of change following the fluid parcel u dot del. So, there is an advective component and then there is an unsteady component plus rho divergence of u is equal to 0. So, now if you were to combine these two, you have the mass conservation statement takes the following form. Dou rho dou t plus divergence of rho times u is equal to 0. So, this, as you can see, gives you that at a given point in space, at a given instant in time, I can relate the rate of change of density with the divergence of the velocity field and gradients of density fields. Because divergence of rho times u is actually rho times del dot u and u dot del rho. So, this was a derivation which is done by considering the material approach, that you consider a patch of fluid and you move along with that patch of fluid. So, mass in that patch of fluid does not change. So, now if I were to relate how density evolution will happen in that patch of fluid, it is related to how the velocity field varies in terms of spatial variations. You could also get this from an Eulerian approach. So, this for those who might have done an introductory course in fluid mechanics, you might have encountered a version of this which is known as the Reynolds Transport Theorem. What it just says is, I will choose a Reynolds Transport Theorem for a fixed region in space. So, if I just choose a fixed region in space, the region in space is not changing. I have decided that this is a fixed volume in space, which means stuff can come in and stuff can leave. There are no boundaries to this region in space. I have just identified some volume in space and this volume is fixed. So, the Reynolds Transport Theorem tells us that the rate of change of mass inside that control volume is balanced by the amount of stuff that leaks in. I am using S, so let me stick to S. The amount of stuff that leaks in or leaks out of that control volume through its control surface. So, you define a region in space. The moment you define a region in space, there is an associated surface that is enclosing that space. So, now if you track how much mass is actually increasing or decreasing in that space, that is related to the amount of fluid that is entering and the amount of fluid that is exiting. Now, because this volume is fixed in space, I can take this derivative inside, in which case this becomes dou rho dou t dV plus rho u dot n dA. This is over a volume and this is over the surface. This should be equal to 0 because there are no source of mass or sinks of mass inside the problem. Now, if I now use divergence theorem, because this is a surface integral, if I apply a divergence theorem, so I have dou rho dou t dV and rho u dot n over the surface area that I have is equal to 0. So, this is dou rho dou t, and on applying the divergence theorem, this can be converted to divergence of rho u dV. Both of these are over the volume. And then you get back your familiar expression that dou rho dou t plus divergence of rho u dV is equal to 0. Now, this should be true for any control volume, any choice of control volume, this should be applicable, right. I have not said what kind of a control volume I have, what kind of a region in space I have chosen. Any choice should give me the same result, which means the integrand should be equal to 0. So, that brings me back to the expression that we have just derived a while back, that mass conservation statement implies that the rate of change of density is related to the divergence. So, either you write it in this particular form or you could also write it in this particular form. So, this is a statement of mass conservation. Now, this basically applies to any kind of flow, any kind of density variation. There is no assumption being made other than the fact that you do not have sources or sinks of mass in the problem. If you were to have sources or sinks of mass in a particular problem, then the right hand side which you have equated to 0, that needs to be replaced with the strength of that source or sink that is there. So, having done this, now we move on to an assumption that we are going to use for the rest of the course, which is an assumption of incompressibility. We are going to consider flows to be incompressible. So, incompressible flows mathematically are flows for which divergence of u is equal to 0. Now, a subset of incompressible flows are constant density flows. So, if rho was spatially and temporally constant, then automatically divergence of u is equal to 0, but that is a subset. What divergence of u tells us is that when you are following a fluid parcel, the density does not change. That does not mean that density is necessarily constant at a particular point in space for all instants in time, or the fact that density is constant everywhere at all instants in time. Following a fluid parcel, density does not change. Now, the correct way to think of incompressible flows would be that density variations or density changes are negligible compared to variations in pressure. So, you have variations in pressure occurring in a system. Would that lead to significant variations in density? If the variations of density were small, even for large variations of pressure, then you could safely consider the system to be incompressible. So, a classic example where this occurs is in the ocean. So, in the ocean, if you take the deepest part of the ocean, so the deepest part of the ocean would be in the Pacific, roughly around 10 kilometers or a little more in depth from the sea surface. We haven't formally written down the equations of motion, but I am assuming you are somewhat familiar with hydrostatic equations. So, hydrostatic equation would tell us that at any depth from the surface, the pressure would be the surface pressure, which if I say is atmospheric pressure, plus rho g h, h is the depth from the surface. So, if I take rho as just for water as 1000, let us assume that it's a constant, g is 10 and it's 10 kilometers, which is 10 to the power 4. So, P minus P atmospheric is around 10 to the power 8 Newton per meter square, which means the pressure at the deepest point in the ocean is around 1000 times, approximately 1000 times atmospheric pressure. Atmospheric pressure is 10 to the power 5 Newton per meter square, which means at the deepest point you have 1000 times the atmospheric pressure, which is huge. It's really a large value of pressure, which is why if you have to design submersible vehicles which can access the deepest part of the ocean, you have to spend a lot of effort in the designing process. So, if you were to design vehicles which can access the deepest part of the ocean, you really need to spend a lot of effort in the material design, something that can withstand such high values of pressure. But if you measure the density at the deepest part of the ocean, this is only has an increase which is around 5% higher than the surface. So the density change over that 10 kilometer depth from the surface density is a mere 5%, whereas the pressure variation is 1000 times. So you can see that there is not any correlation per se in terms of how much does density actually vary. Yes, density is higher there. It is higher by 5% because the pressure is so high. But this has come about because the fluid is almost incompressible. That doesn't mean that density is a constant. There is a density variation that is there in the ocean. If you measure the density, there is going to be a variation of density, and that variation of density is very crucial. If the ocean was a constant density fluid, the world that we live in would be very different. So ocean has a variation in density which plays a big role in the dynamics. But for the time being, what we are trying to understand here is that it is not constant density, and the fact that you also don't see such large changes in density is with the fact that the system is nearly incompressible. So it is perfectly fine to treat it as nearly incompressible because you don't have such strong relations for variations of density with variations in pressure. Now the story is a little different for the atmosphere. Because for the atmosphere, if you were to treat it as an ideal gas, let's say you start with an assumption that it is an ideal gas, then we know that variations in density would give rise to variations in pressure and vice versa. That if you have variations in pressure, you would correspondingly expect variations in density. So yes, incompressible effects would start to show deviations. You would start seeing compressible effects when you are exploring the flow dynamics that is happening in the atmosphere. But you really need to go very high in the atmosphere and look at very large distances over which you will see these compressible effects. If you were to actually observe motion close to the surface, let's say a few kilometers within the ground level, it would be a reasonable model to consider the flow there to be perfectly incompressible. Compressible effects would only come in when you have moved several kilometers, tens of kilometers away from the ground level and you are considering an air column which is extremely tall. That's when you would start actually thinking of what the compressible effects would do. So another way to think of all of this is what we are doing here. If you look at this, we have a term here which is 1 by rho d rho dt, that is equal to minus divergence of u. So 1 by rho d rho dt, this gives me how much of density variations are occurring over the mean. If you think of this particular quantity that you have, going back to the problem of the ocean, there is a 5% variation of density over the mean value. The mean value is around 1000. So when you have a 5% variation over the mean value, even if you take, let's say, seawater will be a little more than 1000. So even if you take that 5% change in the value of density, it's still insignificant or it's very small compared to the reference value. So what you are trying to do here is that delta rho by some mean rho naught, this is actually quite small. You have very small variations that are occurring for density with respect to its mean value. Another way to also think of this particular aspect is if you use the fact that any variations in pressure would be basically transmitted in the form of sound wave. So now we haven't yet again done the momentum equation, but pressure variations in a fluid, you can write it in terms of a scale which would depend on a reference density and a flow velocity scale. So delta P, a pressure jump or pressure variation in a flow, would be associated with the reference density value and a reference flow scale value u. So if you do this, you have u naught rho naught u square, Cs is the speed of sound, delta rho. So what we are saying is delta rho by rho naught, which is the change in density variation, or the density variation by the reference density, is approximately u square by Cs square. How fast is the flow with respect to speed of sound in that medium? That decides how much of a density variation would you observe with respect to the reference density. So when we are saying that the incompressibility assumption is reliant on the fact that you have negligible density variation with respect to the mean density, that is implicitly saying that the speed of flow that you have in the problem is significantly small when compared to the speed of sound in that medium. So in a liquid like medium, the speed of sound would be few thousands meter per second. So when you are looking at flow speeds at those levels that we are thinking of in the context of, let's say, in the ocean, you are never going to encounter compressible effects. It will take a lot for you to experience compressible effects. But then the situation is a little different when you are thinking of the atmosphere, because the speed of sound is around 300 meter per second. So if you have objects that are moving at, let's say, 100 meter per second, which is around 0.3 Mach, then you are going to start thinking about, are there compressible effects that are important? Is it safe to actually still consider the flow as given by divergence of u equal to 0? So this is the perspective which you should have, that incompressibility is a limit. Every flow, every fluid is compressible. Every fluid will have some compressibility. Whether the flow is incompressible, so I am making a distinction between every fluid being compressible to the fact that whether the flow is incompressible, that depends on the fact that whether you have significant variations in density in the flow because of similar variations in pressure. So the checks that you will often be doing is, first you check that are the velocity scales that you are expecting in the problem comparable to speed of sound in that medium. That's an easy check to do automatically, and then immediately negate the fact whether you are going to think of compressible effects. So don't immediately jump to the conclusion that incompressible flow implies that the flow is obviously going to have constant density, because you will see exceptions to that particular rule. The variations of density with respect to a mean value, that's going to be small. So that what that does is it took an equation which was an evolution equation for density. See, if you remember, the mass conservation equation that we had was an evolution equation for density. In time, density is going to evolve due to gradients in density and divergence of velocity. With the incompressibility assumption, you arrive at a constraint. The flow will do whatever it does based on what we will learn in the momentum equation, but it has to obey this particular constraint. So what was earlier an evolution equation for density has now turned into a constraint that the velocity field needs to obey for all times. So this is what makes the idea of incompressibility a very unique idea in terms of how we think of flows. That we will have flows that are dictated by the force balance that we will learn, but at every instant of time, the velocity field that you have should satisfy a zero divergence criteria. And this, as you will also see as we go forward, in the original mass conservation equation, you had a evolution of density field. Now, when we will learn the momentum equation, we will see that there is a role that pressure plays in terms of how it forces the flow. So what you would have required additionally is an equation of state that given a particular value of density. So think of the example of, again I am going back to the example of an ideal gas. So if you say that P equal to rho RT, rho being the density, T being the temperature up in Kelvin, and R being the normalized absolute gas constant. So, if you take the ideal gas equation, given the value of density, you have a corresponding value of pressure, and then you use that value of pressure in terms of plugging it into your momentum equations. So, which means the absolute value of pressure is important. The value of pressure at a given point in space is given by the value of density at that particular point in space. If you just take the bare minimum, which is the ideal gas. When you are going to use the incompressibility, you will finally realize that the absolute value of pressure has no role to play in the dynamics. What would matter is the gradient in pressure. Whether you say pressure is a constant plus something that is varying linearly with position, or you change and make it twice that constant by this plus the same linear variation in spatial coordinate, it will not change the dynamics. So, a datum value of pressure or a actual value of pressure, that doesn't really matter. What matters are variations the moment you do incompressibility. So, these things start to basically get combined together when we look into the momentum equation later. So, right now we will continue a little bit with incompressibility. So, we have learned that there are flows which are incompressible, that is given by that the velocity field is divergence free. Now, during our discussion on tensors, we had few problems that we did, and one of the problems that we did was that curl of a gradient is always equal to 0 and divergence of a curl is also equal to 0. These were identities which we proved using tensors. So, now because every vector field which can be expressed as a curl of another vector field will always be divergence free, which means if velocity is a divergence free vector field, we can write it as curl of another vector field. Now, this is an idea which is not specific to fluid mechanics. This is true for any vector field. This is used in the idea of magnetic field. Magnetic field is another vector field which is divergence free, which can thus be written as a curl of another vector potential. So, now because this is curl of any vector field, I can write this vector field using the first property as a combination of two scalar potential. Because if you remember, if I take curl of A, I am basically going to have zeta curl of grad psi plus grad zeta cross product with grad psi. Now, this is 0. So, I can express that vector potential in terms of two scalar potentials. So, my first statement was that you have a divergence free vector field, which means that that vector field can be expressed in terms of a curl of another vector field, and that additional vector field now I am expressing in terms of combination of two scalar potentials, zeta and psi, which means my velocity field can be written as grad zeta cross grad psi. So, visually what does this do for us? So, if you draw, let us say surfaces of let me use a. So, we will try to visualize what this looks like. So, I will first draw surfaces of constant zeta. So, imagine each of these surfaces are surfaces of zeta equals to constant. And then I will draw surfaces of constant psi. Streamlines are going to basically be located at the intersection of these two surfaces. So, you imagine your space is basically made up of these families of surfaces, one being surfaces of constant xi and the other being surfaces of constant psi. The intersection of these surfaces gives you your streamlines. So, you have a velocity field which has 3 components in 3D, but it has to be divergence free, which means they cannot be arbitrary. There is a constraint on that velocity field. So, by being divergence free, you impose a constraint that the velocity field that you are looking at, the component should be related by the relation. If I use x, y, z now as Cartesian components and u, v, w as my velocity components along x, y, z, it should satisfy this. That is divergence of the velocity field expanded out in Cartesian components. So, now what it says is that the streamlines that you have in this problem are basically going to thread intersections of sheets of constant zeta and constant psi. This is what you will happen for any 3-dimensional incompressible flow. So, this is basically for any 3-dimensional incompressible flows. So, to define any 3-dimensional incompressible flows, you need 2 scalar potentials. You can try to preempt that, right, that the velocity field has 3 components. If there is a constraint, then you can't get to choose all 3 components independently. You can choose 2 components independently and the third one gets determined from the incompressibility constraint. So, that is basically what I am writing out here, that there are these 2 scalar functions which you can choose independently, and when you choose them independently, the surfaces that constitute these 2 surfaces will actually help you construct the velocity field. Now, this gets particularly simpler if the flow had certain symmetries or simplifications. So, the first simplification that we will consider is if the flow was 2-dimensional or planar flows. So, the flow resides on a surface. Now, I am going to consider the surface to be spanned by the x and y axis and the normal to the surface being z axis. So, here what I will do, I will choose one of those scalar functions as z. I have chosen minus z, it is a convention and later the convention will get clearer why I am using this particular convention, which means grad zeta is going to be minus z hat, which is the unit vector. Z hat is the unit vector along the z axis. So, the velocity field, which is defined as gradient of the scalar function zeta cross gradient of psi, this becomes minus z hat cross grad psi. Or you can also write it as grad psi cross product with z hat. So, if you now write the component of this, u will be dou psi dou y and v is going to be minus dou psi dou x. So, there is a single scalar function which is going to define any 2-dimensional flow, and psi is what is known as a stream function. So, for the 3-dimensional problem, it can get a little difficult to visualize, because now you are thinking of 2 families of surfaces that are intersecting and streamlines are going to thread those intersection. When you come to 2D flows, then you just have this one single function psi which gives you the two components of the velocity field. Now, what is the connection of the stream function with the streamlines? So, if I write d psi, which means a small change in psi. Psi is a function of x and y. So, a small change in psi would be dou psi dou x dx plus dou psi dou y dy. Now, substitute from the relation in terms of velocity. So, dou psi dou x is minus v dx, dou psi dou y is u dy. This is, if you remember, u cross dx, the vector or the line element, its z component. So, along a streamline, we know u cross dx is equal to 0, because streamlines are tangential to, or the velocity vector is tangent to at any point on the streamline. So, along a streamline u cross dx is equal to 0, we have d psi is equal to 0 or psi is equal to constant. So, what we have seen now, that psi or the stream function is a constant along a streamline. This is a very interesting relation that you have now. So, what you started out was, there was a mass conservation statement that reduced to, for a certain variation restriction of density, to a divergence criteria. That became a kinematic constraint, divergence of u. And now, because you have the flow being divergence free, you have the fact that the velocity field can be expressed in terms of combinations of two scalar functions. Further, if you say that the flow field is two-dimensional, so it resides on sheets which are perpendicular to the z axis. So, I have chosen the two-dimensional to be parallel sheets, and each sheet is basically perpendicular to the z axis. Then you have one single quantity, which is a stream function that defines the entire flow, and this stream function is a constant along a streamline. So, this can now further be reconciled with what we learned about mass conservation. So, if I draw two streamlines, so along this particular streamline, psi is going to be a constant. So, I will choose a point B. So, psi is equal to psi B, and it remains a constant everywhere on this line. And similarly, I will choose another point A, and the streamline or the stream function takes a value psi is equal to psi A on this particular streamline. Now, if I try to draw a line, this is not a streamline, this is just a line that I have drawn connecting the two streamlines, and this is x and this is the y axis. So, if I try calculating the mass flow rate through that line, so this is the rate of change of, or the mass that is entering or leaving that. So, it would be rho u dot n dA over this strip going from A to B. So, if the velocity is directed inwards x, the normal is outside. So, this is minus A to B rho dy, and if there is a width that is coming out of the plane, that would be w. Sorry, I have used w for vertical velocity. So, let me just say h maybe. H is a distance that is coming out. So, mass flow rate per unit depth is going to be minus A to B rho u dy. considering rho to be constant. If I substitute for u, so I have A to B dou psi dou y dy, which means m dot per unit depth is minus rho psi at point B, which is psi B minus psi A, or rho of psi A minus psi B. So, the mass flow rate that is basically going through the region that has two streamlines on either side is basically the difference of the value of the stream function on those two lines. So, you can imagine that there are these lines which are actually fictitious lines. I mean, the lines are basically for our visualization. There are no true boundaries on that line. So, the mass flow rate that is actually going through this is just the difference of the stream function on those two streamlines. This is actually mass flow rate per unit depth. Now, if you were to, let us say, find the mass flow rate by drawing a line that is parallel to the x-axis. So, I chose a point B here and I chose a point C here. So, point B and C have the same y coordinate, but they have different x coordinate. So, if I try to now find the mass flow rate that is leaving that line BC, so I will integrate from B to C rho u dot n dA. Now, here the velocity is in the y direction, which is pointing out, and the normal is also pointing out. So, m dot BC is going to be B to C rho V dy. This is again per unit depth. Now, V, as we saw, is minus dou psi dou x. So, V is dou psi, this should be dx. You are integrating over x. So, minus rho dou psi dou x dx, which if you integrate, you are going to get minus rho psi c minus psi b. So, this psi c is the same as psi a. The value of the stream function at the point C should be the same as the value of the stream function at point A, because it is on the same streamline, which means m dot BC is going to be rho minus rho psi A minus psi B. The amount that is entering is rho psi A minus psi B. So, the amount that enters is exactly the amount that enters through AB is exactly the amount that is exiting through BC, which is perfectly consistent because this line segment AC, now if you think of this as an entire control volume, the line segment AC is a streamline, and the definition of streamline is there cannot be any normal flow. The velocity is always tangential to the streamline. So, whatever comes in through AB has to leave through BC. So, this is just a confirmation of that. So, what you have now seen is that the stream function has a meaning. The stream function, besides giving you the velocity field, besides being that scalar function that gives you all two-dimensional incompressible flow, it is also related to the mass flow rate per unit depth. So, when you see pictures, let us say from simulations or images, and you see streamlines and you see either them bunching up in some place or them fanning out in some place, it tries to give you an idea of what is the mass flow rate, how much of fluid is actually being transferred, or without the density, the volume flow rate. So, if you do not have the rho, so just psi b minus psi a or psi a minus psi b, the change in the difference in the stream function will be the volume flow rate per unit depth. So, We started out by saying that for any arbitrary three-dimensional flow, this is the relation. Then we took a detour and we said, let's consider 2D flows which are planar, and in that case we have the following relation, and we arrived at u, the x component is dou psi dou y and the y component is minus dou psi dou x. Now, there is also another class of flows where you can think of the problem being two-dimensional. The other class of flows where you can think of the problem being two-dimensional is if the flow is axisymmetric, which means the flow looks identical about the axis of symmetry. Think of a flow through a tube. There is a flow through a pipe or a flow through a tube. So, if you define an angle which is, let us say, phi about the symmetry axis, whichever angle that you look, whatever values of phi that you are looking at, the flow looks identical. So, axisymmetric flows are another example where you can think of that there is a reduction in dimensionality. So, by that thinking of that reduction of dimensionality, here I can define my zeta, which was in the previous case zeta was minus z. Here I will define zeta as minus phi. Phi is the azimuthal angle that you have. So, if zeta is minus phi, then gradient of zeta is minus 1 over r phi cap. So, you apply it to the formula for u. So, u is going to be minus r phi cap cross gradient psi. So, in cylindrical coordinate, the radial component of velocity would be minus 1 over r dou psi dou z, and uz is going to be plus 1 over r dou psi dou r. So, dimensionally you can see it is a little different than what you had in the planar problem. So, this psi which appears in any problem that is axisymmetric is known as the Stokes stream function. So, any axisymmetric problem could be flow through a pipe. You can also think of smoke rings or vortex rings. So, if you imagine that there are these puffs of smoke that goes into this toroidal kind of shapes, those are also axisymmetric. Any rotational flow, that is also axisymmetric. So, a lot of axisymmetric flows will have this dimensionality reduction because the flow is invariant about this azimuthal angle, about the axis of symmetry, in which case you can also reduce the problem to studying one single object, the Stokes stream function. You are thinking of flow due to a translating sphere, that is also axisymmetric. So, this is basically where you started out with an idea of mass conservation. The starting point was saying that variations in density is related to gradients in density and divergence of velocity. Then with incompressibility, we arrived at divergence of u is equal to 0. That was the constraint that the flow needs to obey. And then because of this constraint, we got introduced to the fact that there can be an object in 2D incompressible flow, which is the stream function. So, often we will keep doing this switch. In certain problems, the stream function gives us an economical way of looking at flows. So, that is what we will do after we finish momentum equation. So, with that we will close here, and in next lecture we will get started with the next conservation law, which is conservation of momentum. Okay.